So I'm going to talk to you guys a little bit about a model we've been working on for a while. We call it the dynamic vacuum model. And we categorize this as a pilot wave theory. We have a lot of the same thought processes that we've heard discussed. In a lot of cases applied to the walking droplets, but we tend to go directly towards some application of things like the hydrogen atom. But the central theme of our approach, if you will, is that the quantum vacuum is a dynamic medium, meaning that it can vary in space and time. And as such, it can support longitudinal wave modes. And so that means that whatever it's made of, quantum vacuum fluctuations, what have you, the internal constituents are capable of interacting and exchanging momentum. And so some of the stuff I'm going to talk to you about today is some of the work we've done studying the hydrogen atom, and then leaning a little further forward into thinking about chemistry. We did a very light survey of nuclear physics, and then had a little bit of a surprise finding on gravity, if you will, kind of expanding this dynamic vacuum thought process. So we went through the process of deriving the acoustic wave equation from Schrodinger. I'll go through that in a few slides here. And so in the process of doing that, established a kind of a logic framework that says electron orbitals can be viewed as acoustic resonances in this dynamic vacuum. When I say acoustic resonances, I just mean to say longitudinal wave resonances in this dynamic vacuum medium. So this is all documented in our paper that's published in Physics Open back in 2019, where we went through a process of deriving the acoustic wave equation from the Schrodinger equation. And we take the path by going through the Madelung equations. I think most folks on this conference are familiar with his work. I think for me, in my own process of exploring the history of the pilot wave approach and some of the debates and discussions that have occurred over the years on it, in some ways, just going through this little exercise here, it's surprising to see that if we change the Schrodinger equation to polar form, and then we separate that expanded form into its real and imaginary parts, we've got this term that appears naturally here, and that's identified as the quantum potential. And I know in the process of becoming more familiar with the pilot wave theory over the last several years, that there's been objections raised to the premise of the quantum potential Q. And it's, to me, in the process of going through this, it's almost like it's inherently implied in the Schrodinger equation. It just requires a coordinate system change to make its effects more directly mathematically implicit in the equations. So anyway, that's just something I found interesting, that whether people like the pilot wave approach or not, it's almost like the premise of the quantum potential is embedded in the Schrodinger equation. But we can go through a process following Madelung, where we end up with these quantum Euler-like equations. Can people see my mouse when I move it over the screen?
Yeah. Yeah.
Right. And so again, we're just at this point, we're just duplicating what Madelung did. But now we make the next step to try and turn these into a continuity equation, a force equation, by making the substitution rho m is equal to m times the probability density. And then we have these two equations, the continuity equation and force equation. And then we can follow a very textbook approach to try and derive an acoustic wave equation for these two equations by basically putting a perturbation into the system, introducing the instantaneous fluid density, the equilibrium density. And we, of course, have the condensation at a point that represents the variation of the density normalized, the instantaneous pressure and the equilibrium pressure, and then most importantly, the acoustic pressure, which is the difference between the two. And then C sub s is the propagation speed of the longitudinal wave through that medium. And so we can go through the process of assuming that the waves are small, kind of linearizing these equations, if you will, and go through and simplify these equations a little bit to get to this intermediate form. I'm going to go fairly fast through this. If you really wanted to look through the paper, it's available. You can spend some more time with it. And then we get the equation of state, where we go through and represent the relationship between the total pressure and the mass density as a Taylor series expansion. And again, assuming the magnitude of the waves are small, we only keep the lowest order term, and then we get this equation of state where the bulk modulus is as defined there to the right. And then we can combine these equations to yield the very familiar acoustic wave equation for the system. And of course, if we want to go through and solve for some eigenfrequencies of this system, we can take a look at the Helmholtz equation and then solve for the eigenfrequencies of the system. Now, in order to do that, though, we need to specify a density field and a velocity field for the system. So we take the electrostatic field around the proton and we equate that to a density field using the Einstein mass energy equivalence approach. And then that gives us this 1/r⁴ density field for the vacuum, quantum vacuum that expands out from the proton. And then we derive a speed of the longitudinal waves through that medium. You see there in the right-hand equation. And then we can go through and we can take this system and we can solve for its eigenfrequencies. And in the process of solving for the eigenfrequencies for the system, this is some work we did using COMSOL to find the eigenfrequencies of the system. We find we get the familiar n is equal to 1 orbital with the right energy and probability distribution, and climbing all the way up to n is equal to 7. In addition to the s orbitals, we do see the p orbitals, the d orbitals, and it's not shown here, but we also see the f orbitals. And so a way to think about this, right, like a p orbital in this context being a longitudinal wave resonance of the system, the medium, whatever it is, it's undergoing this azimuthal oscillation about the nodal surface that's kind of represented by that dark area at the center of the p orbital. And so the real electron is embedded in this medium, whatever it is. And the statistics of being able to observe that electron are directly affected by this dynamic of this eigenfrequency of the system undergoing this acoustic resonance. So this is, again, some work we did for DARPA Defense Science Office. We wanted to expand the thought process to see, does the approach potentially show promise to be used for chemistry, if you will. And so we just did an assessment of the hydrogen molecule. We took our density field and velocity field that we showed you previously, and we created a 2-atom system. Where we have 2 atoms in close proximity based on the separation distance for molecular hydrogen, and then go through and calculate the eigenfrequencies for this system using COMSOL. And then this shows the frequency response curve for the system. You see the 2 very large resonances there, and that they are both fairly close to the anticipated energy level for molecular hydrogen. I think the thing for me, right, that's also interesting about some of the work that we did for the hydrogen atom and then for molecular hydrogen, right? The premise of quantization, right? It's just it's a natural response of the system because of the frequency response curve. Those are the only ways in which the system can interact. Everything else is just completely reflected, if you will. There's no interaction at any other energy levels except for those resonances according to the frequency response curve. So in my mind, it provides a little bit more of a natural understanding of the premise of quantization. This is not published. This is just some early work that we did just to try and go through and see if we could go the other direction instead of looking at molecular chemistry. Could we potentially take a simplistic approach of looking at a Woods-Saxon potential and derive a density field and a velocity field for the proton? And so in the process of deriving a density field and a velocity field for the proton, we actually have 2 models we looked at. We can look at the eigenfrequency for this system. And of course, the frequency is where we want it to be. And then as you see from the acoustic response here, it's got this, obviously this interesting negative pressure that seems to have some qualitative similarities to some results that were published in the literature using lattice quantum chromodynamics. But again, this is just an early assessment. There's a lot more work to go do. Just it was an interesting finding, and so I'm sharing it with you guys. You know, the I guess the question is, so what, right? You know, this is all interesting and fine and dandy, but why would we really even care about this? In some ways, it could be said, I mean, we derived the acoustic wave equation from Schrodinger, so we shouldn't be surprised that we found that the electron orbitals are acoustic resonances of some type of a system, because we derived the acoustic wave equation from Schrodinger. So what? But I think that the point is the acoustic oscillations, right? They require variation in some type of a medium to be able to be manifest. They have to have a densification or rarefication both in space and time. And so that means that whenever we try and find the eigenfrequencies of the hydrogen atom, we have to specify a density field and a velocity field to be able to find those eigenfrequencies. So in some ways, you know, in my mind, maybe this is starting to establish the premise that the concept of the pilot wave approach versus the Copenhagen approach to quantum mechanics, instead of just being this this view of, well, that they both represent the same thing, right? One person likes vanilla ice cream and another person likes strawberry ice cream. They're both ice cream. You just pick whichever mathematical framework you want to work in. But I think it may be a little bit more fundamental, right? That maybe Copenhagen is incomplete. I know there's probably some folks on this line that may say stuff a little bit stronger than that, but that's about as strong as I'm willing to go right now. But you know, I think maybe Copenhagen is incomplete, and the pilot wave approach is more fundamental, right? And it may be making predictions. It may be possible for pilot wave approaches to make predictions that the Copenhagen A doesn't make, and B in some cases won't even allow, right? Because I think it might be meaningless in the Copenhagen interpretation to ask what's the density field around the hydrogen atom. And I know with like the double slit experiment, Bohmian trajectories are also something that Copenhagen interpretation would not predict. So this next part, this is not published yet in a paper. This is some work we did in extension of the work we did with at the microscopic level. We've long speculated that gravity is an emergent phenomena. And so my analyst had been bugging me for quite some time while we were doing the work on the hydrogen atom and the molecular hydrogen. Can we derive a density field and a velocity field for the sun's gravitational potential using the same technique we did for the other potentials? And so I finally went to the trouble to do that just to satisfy him. And I didn't expect to find any type of correlation or anything interesting. I thought it would just be a fun exercise, but there would be nothing that came out of it. And so we implemented a model in COMSOL, and unfortunately, because of the size and the scale of this, it does take a lot of computational capability to do this, like thousands of CPUs. Input a density field and a velocity field, and then put in a perturbation for the system to find the eigenfrequencies. I'm just kind of skimming through the model, but when we look for the eigenfrequencies that correlated to the known planetary orbits, we found eigenfrequencies that correlated to all of the planets in their slots, including Ceres, right, in between Mars and Jupiter. And so, looking at the errors here, right, you can see we found. I mean, I was surprised to find that. We really did not expect to find that correlation. But what we speculate may be going on here is that maybe gravity has, if it is this emergent phenomena, this alternate viewpoint of things, maybe there is a soft quantization to the concept of planetary orbits. The frequency response curves, you can see the frequency response curves that are there, and so that would suggest that in a star's dust disk that's around it as the planets start to coalesce, it would seem that maybe the potential has record grooves, if you will, very small subpotentials, if you will, because of these frequency response curves that will statistically have a larger likelihood of coalescing a planet. And so I think one of the things we'd really like to do is to take this approach and model, go look at the exoplanet database, and we can look at the different stars that have planets that they've found, and then go through and do this type of analysis for those to see, do we see some type of statistical correlation with what the modeling approach that we're taking relative to the planets that have been found around the different stars. And maybe if we were able to show that, this technique might be used in the process of trying to find future exoplanets, right? We could help investigators maybe narrow their search to specific frequency bins, if you will, and maybe it's something where there's a 67% chance that they would find something. I think the one additional thing that we think that we need to understand with this is, I think there's also obviously planetary interaction. So I think we're trying to figure out how would we combine the frequency response curves so that if a planet's already in orbit, how does it affect the other record groups that are around it, right? Is it going to mute certain locations and increase certain locations where they have more appeal, if you will, in terms of how does the field communicate to, the presence of one planet affecting all the other record groups that are supposed to be around the star. So again, who cares, right? This is some interesting stuff. Actually, I think this is just a repeat slide here. Sorry about that. Again, I think this is maybe building the argument that pilot wave approaches are maybe more fundamental than what people, it's not this ontological, it's fundamental. So now I'm going to switch gears and talk a little bit about application. We here at Limitless Space Institute, we do want to think about ways that we can try and leverage some fundamental physics in ways that maybe we can come up with some approaches that might be useful for technological applications. In our case, with an interest towards space, but currently the work that we're doing to explore our physics model is how it applies to Casimir cavities. The dynamic vacuum model suggests that the state of the negative vacuum energy density that's predicted to exist in a Casimir cavity is not this isotropic state. There's actually some spatial variation to it in between just a garden variety parallel plate Casimir cavity. There's structure to the quantum vacuum that's in between those two plates, and that structure has the potential to generate in like the picture on the left there, maybe a very small polarization field that we could detect with some very sensitive equipment. Maybe we can generate longitudinal waves in the quantum vacuum, and maybe this might be something of value in the context of communications or sensors, right? So having some tapered cavities, that's another area we're trying to explore. And so this is some direct application of the thought process to some technological devices that we're trying to study and model and manufacture, because the dimensions of these things have to be very, very small to generate magnitudes of signals that we might have a chance of being able to detect in the laboratory. And you see two different examples there on the left. This is some nanofabrication that's been done by some of our team members at Texas A&M using a NanoScribe GT 3D printer. And these, the separation distance between that wall and the pin there is about 2 microns. So the total gap is about 6 microns, 7 microns plate to plate. We want to get smaller, but we're still trying to learn how to make these things. And then we go through and we plate this material with metal, so everything gets metallized as well. On the right-hand side, this is using a more, sorry, I'm moving my mouse on the wrong side. On the right-hand side, this is using a standardized etching technique to go through and etch a silicon wafer to implement, plate pillar cavities, if you will. And this is not meant to be a device that we're going to test. We're still working out the manufacturing techniques to see if we can create the features that we're at the size we're trying to make. Now, in terms of the approach that we're taking to model the perturbation of the quantum vacuum, in the process of doing some literature search, we found a very useful technique that was pioneered by Holger Geiss in 2003 called the Numeric Worldline approach to calculating the Casimir phenomena. And this was interesting to us because this technique also predicts this spatial variation that we anticipate exists in a Casimir cavity based on some earlier work with the dynamic vacuum. And so this uses an effective action approach to calculate the energy density distribution. If I could kind of articulate the muffin making recipe relatively simply, the algorithm generates an ensemble of unit loop world lines that are representations of a massless scalar field. And so you have an ensemble of 500 loops, 1,000 loops, 1,500 loops, whatever your computational assets can support, where more is better. And it moves this unit loop ensemble to different points in the model, and then expands those unit loops by scaling them with a proper time t, so that makes them, instead of just being unit loops, and they get physical energy associated with them, until such time as that scalar vacuum field fluctuation pierces 2 or more potentials in the model. And then that allows us to go through and increase calculate the contribution to the energy density for that particular vacuum fluctuation. And then we can do that across the whole ensemble and at all the different points in the model. And then that's what helps us understand what the predicted response of the quantum vacuum is to those potentials. And so the technique we use to generate the scalar field vacuum fluctuations, it's a V-loop method. Again, that was pioneered by Holger Geis. It's a Gaussian distributed closed unit loop, again, representative of a massless scalar field fluctuation. And these are the pictures that kind of go with those words, right? Where we've got this ensemble of scalar field vacuum fluctuations. We move them to different points in the model. Here you see, this is just like a parallel plate cavity. We would move the vacuum fluctuations to a particular point in space, and then we would scale them until such time as the collision algorithm detects that the fluctuation pierces the potentials, and then that actually makes a contribution at that point in the model based on the scale at which that fluctuation pierced the potentials. And then we can go through and we can calculate the predicted vacuum response to any arbitrary shape. That's the real power of this technique is, I mean, you can do it in 2D if your model is amenable to 2D, but it's very powerful from the standpoint it can do full 3D, which is why we were kind of drawn to it. Not only does it do arbitrary shapes, it handles edge effects, right? So a lot of times in the process of calculating the Casimir phenomena, you just assume infinite plates, but this can deal with finite geometries, and you can see how the perturbation of the quantum vacuum expands into free space. And here you have the sphere plate scenario where you've got this energy density distribution that expands out into free space. And of course, this model doesn't care about edge effects, so it can do a blade plate case. So you can go through and see how even with an infinite curvature, if you were with a curvature of 0 here, and you can also see the evanescent fields. How does the field expand into the structure itself? And so we found this to be a very useful technique, and so we've implemented it and validated it against the stuff that was done in the literature to show that it correctly predicts the Casimir force for all the standard analytic models. And so then we've adapted the approach to model how the quantum vacuum responds for our pillar plate cavities. In this case, I'm looking at the parallel plate cavity. You can see the predicted response of the quantum vacuum to the presence of these potentials. And so we can go through and use this and come up with a prediction for the polarization field in the quantum vacuum to come up with an expectation of what the voltage potential might be, even though it's very small, what the voltage potential might be between the pillar channel and the plate channel. So in this case, for the as-built picture that I showed you, this is predicting a 50 microvolt potential between the pillar and the wall. And so that's something we're gonna try and see if we can't study using an atomic force microscope to map out, see if we can see the polarization field using the Kelvin probe force microscopy approach. And then maybe we can also try and directly measure the signal using some very sensitive electronics equipment. Now the parallel plate cavities, let me move this a little slower. The tapered plate approach. We can go through and model the response of the quantum vacuum to the tapered approach using this numeric Worldline technique, and you can kind of see the This three-dimensional model shows the field expanding out into free space, and we get this energy density distribution. And you can also see evanescent fields that expand into the structure itself. And so we can go through it. In this particular model, this is 4 microns at the small end, 6 microns at the big end, and then these plates are basically 40 microns by 40 microns. And so we can go through and calculate the energy density distribution. And then we can import this into COMSOL and come up with a force distribution across the bounding surfaces to go through and calculate the Casimir force. And we can do that in all 3 axes as well, right? There's this is because these plates are tapered, there's also a Casimir force in this direction as well. But the thing that we're curious about, right, is thinking back to the logic that we established with the hydrogen atom, right? That this dynamic vacuum can support longitudinal waves. So that means that the stuff that makes it up is capable of interacting and exchanging momentum and energy. And so if we have this asymmetric energy density and pressure field established in the quantum vacuum in response to the presence of these 2 plates, is there potentially some kind of a velocity field coupled to this, the presence of this asymmetric density and pressure? And so we can go through and we can import this data into COMSOL, and then we can go through and establish the appropriate boundary conditions. And I just want to say this is this is not a new idea. It's been thought of before. There's another team that recently published a paper in Science Advances trying to model the Casimir force for parallel plate cavities as being a result of isotropic turbulence in some kind of an underlying field. And so that was some interesting work. And I think Paul Stevenson's documented a lot of stuff in the literature studying hydrodynamics of the vacuum, thinking about things in that context. And of course, John Bush and the stuff we heard yesterday on the hydrodynamic quantum field theory with Yuval Dagan's presentation. So it's, I think this, you can certainly see why we're very interested in John's work as well. But when we go through and we establish the appropriate boundary conditions for this system, and then we run the analysis, we've run it in both the laminar flow module and the turbulent flow module, just to see if there were differences, if you will. And so we model it where we have no slip on the cavity walls. This is that tapered cavity. There's a velocity field associated with that energy density distribution imported into COMSOL. This is where the streamlines, you start them at the back of the control volume and work them forward. And this is where you start the flow lines, the front of the control volume, and work them backwards. This is the exact same case. It's just looking at the flow lines originating from one end of the box or the other end of the box. Now, I think the other thing that was interesting is there's this interesting peak in velocity well outside the mouth of the cavity itself. But these velocities are very, very small. These are like micrometers per second. So this is not a very fast flow, if you will, but it is non-zero based on importing this stuff into COMSOL, and it would be required to preserve this energy density distribution. Now, when we look at it in the turbulent mode, and so this is the laminar flow on the left. This is the turbulent flow on the right. There's not a drastic difference between the two, but there is a difference. You can see that they both have that interesting peak in velocity well outside the opening of the cavity. I don't know if that would mean maybe there could be some optical properties we could explore. I'm not sure, but it's just at least from an analytic perspective, it's a numerical analysis perspective, it's interesting to us. And this is just showing a slightly different coloration of the same system. And then a zoom up of the this weird focus point in front of the cavity. You can kind of see some of the back and forth between the 2 plates there of the system. This just shows our lab here that we have. We have a Space Act agreement with NASA, so I have all my equipment from NASA. And we did pick up an atomic force microscope, the Cypher S atomic force microscope. It's been used extensively in the process of studying the Casimir phenomena. So it has a lot of history with that. And so we're partnered with some other folks that have this same atomic force microscope and use it to measure the Casimir force phenomena. So we could measure the forces directly by having, say, a colloidal probe that we would move around the opening of, say, like the parallel plate cavity, if you will. And we can use our numeric Worldline technique to come up with a prediction for the force to show that the negative vacuum energy density that exists between the plate, pillar plate, and a spherical probe in close proximity to go through and show that do we see this spatial variation in the energy density that we're predicting. We could go through and maybe create a two-dimensional map of the forces at a particular location up from the opening of the cavity. We could also use the Kelvin probe force microscopy to go through and try and measure the polarization fields to see if they correlate with what we think may exist based on our analysis. We have a very precise oscilloscope that can sample it 20 gigasamples per second. So we could potentially measure small, the small voltage, the transient voltage signal that we think may exist. Alternately, we could use a 4-point probes method to try and measure ineffective conductivity of the cavity, if you will. And so that would allow us to measure, very, very small voltage pulses and currents down to the nanoamp level. So maybe we could gang some of these together on a chip to try and get to a point where we could use that technique. And so with that, that's my talk. I think I'm 1.5 minutes over. I apologize.